So this video is aimed at students that are about to sit the OCR GCSE Computer Science Paper 1 exam. The idea is it's not a complete revision guide by any sort of imagination. It's going to cover list really the topics that you need to know about, maybe look at some of the common misconceptions and go through some short example questions. Much of the slideshow is going to be just showing pictures of the specification. If you want to see the full copy of this, you can Google for it and download the full specification. The best way to use this video would be to pause the video every now and again and maybe just make some quick notes of any of the topics you feel you need to go away and do further revision on. Okay, let's get started. The first topic is the architecture of the CPU and is really fundamental around how a computer works. It uses something called the fetch execute cycle, where computer programs are stored in the primary memory of the computer, generally RAM or ROM. These are then fetched from that RAM or ROM to the CPU, ready to be decoded and executed. You need to be aware of the main components of the CPU, such as the arithmetic logic unit, where the execution sort of happens, control unit, where your instructions are decoded. What cache memory is, this is fast memory that is used to keep commonly used instructions so they don't have to keep being fetched from the RAM or ROM, and this speeds up the computer. All of this is only possible by using various registers that you need to be aware of, sometimes known as the von Neumann architecture. Next, you need to sort of think about what are the different characteristics that can affect the performance of the CPU. First one is clock speed, typically measured in gigahertz, and the faster or the higher this number, that means the more times the fetch, decode, execute cycle will complete, and the faster that the performance of the CPU would be. We mentioned that the cache keeps commonly held instructions. If you had a larger size cache, then you'd be able to store more instructions in the CPU, again meaning you may have to do less of the fetching from RAM, which is slower, and this can speed up the operation of the CPU. Finally, if we want to improve the performance of CPUs now, we've had to move to an area where we start having multiple versions of what we call cores, the important parts of a CPU. This allows us to execute more than one instruction at the same time, and obviously would speed up the performance of the CPU. Finally, you just need to know what an embedded system is, a computer that's built into another system, and know some common examples of these, such as engine management systems, microwave ovens. Try and stay clear of the sort of things like fridges and thermostats. These are things that don't always have to be an embedded system. And if you are using some of them, perhaps use the word smart in front of it so it's clear that there is a computer involved in this system. Next topic we need to know about is memory and storage. The first part of this is primary storage. This is the RAM and ROM I was talking about a minute ago, where we fetch and decode and execute the instructions from. You need to know the difference between them. RAM being volatile, meaning it loses its contents when you turn the power off, and it is read-writable, whereas ROM is read-only memory, and the contents can't be changed, and they do not lose the value when the power is removed. Typically, ROM's used in the startup of a computer, or it might be used to hold the programs in an embedded system where we don't need to change them. Main reason for RAM is it's a temporary storage, so we will be loading programs into the RAM before we can start executing them, and we'll be able to store values and that are calculated, etc., during the operation of programs. Finally, we've got virtual memory. This is really just RAM and secondary storage kind of being used so that if we run out of RAM, we can move programs that aren't currently being executed out of the RAM into the secondary storage temporarily to make space for more programs to be loaded. Downside of this, though, it doesn't give us a much larger amount of real RAM. It appears to the system it has more RAM, but it's a lot slower because the moving of programs in and out of the secondary storage, this virtual memory, will slow the system down. Next, our secondary storage. Well, this is a much larger area of storage and is normally permanent storage. Unlike RAM, where we lose the contents, we need somewhere to store programs and data long term. There are three main types of storage devices, and it's important to understand when you see questions if they're looking for types or actual examples of the different types of media. So we know things like a hard drive, an SSD drive, memory stick, example there. If the question is asking for types, you need to be talking about optical, magnetic, and solid state rather than using things like hard drive and USB memory stick. If you want to talk about memory sticks as well, please don't just say that they are USB. Please make sure you put USB memory stick in there. USB on its own as a word or as an acronym is just a way of communicating with things. Typically, though, if you get questions on storage, you might be asked to sort of recommend types of media or a given sort of application. And to do that, you need to think about the different characteristics of memory, its capacity, its speed, how small it is, if it's durable and reliable, how much it costs. So, for example, if you were asked to suggest a media for something like a head camera for when people go skiing, something like a GoPro, you would want something that is definitely small and durable. It would need to have the right sort of capacity and speed for this application. And that would be something like a micro SD card. Next, you need to be aware of the different sizes of capacities, the units of measure, and you need to be able to state them in their order and note that they increase, first of all, from 1 bit to 4 bits, a nibble, not always talked about very often, but the next one after that is 8 bits. Thereafter, 8 bits, which is a byte, we go up in times 1,000 each time, so kilo, mega, giga, tera, peta, etc. You might need to be able to move between these different units, either by dividing by 1,000 or dividing by 8 to go from bytes to kilobytes, or multiply, etc. You've got to be aware of the different ways of different number systems and how we represent them. You should be able to convert between binary and denary easily. You should be able to do addition of binary, understanding the carry bit and showing this if you're asked to calculate it, and you need to be able to do hexadecimal and binary conversions. Finally, you need to understand about shifting of binary. As we move things to the left, we're multiplying by 2, and if we move things to the right, we're dividing by 2. These are really easy questions in the exam if you've practiced them. So if you haven't practiced them, go do some now. Next, we need to understand about the way different types of data is stored for things like characters, images, and sound. So for characters, you need to know about the way each character in a character set is given a unique numeric value, which can be stored in decimal or binary. There's two systems that are commonly used, the ASCII, which is originally has 128, but more recently has 256 characters in it. Problem with that is you can't then represent all of the different character sets that we use around the world. So Unicode was developed to have 16 or 32 bits, which allows a much wider range of characters. You need to know about images. They're stored using the bitmap format, where each of the pixels are represented by a series of bits. So each color that the pixel could be will have a numeric value. Depending on the number of colors, that will sort of change how many bits are required. One system is the RGB system, where we have 8 bits for red, 8 bits for green, and 8 bits for blue. The quality of an image will depend on the number of pixels in that image. The greater the pixels, its resolution, often the better the quality it will be, and the more colors that are in there, the more clearer images will be. However, if you increase either of the bit depth, the color depth, or the resolution, that's going to change the size of the file and make it larger. Similar thing with sound. So sound is stored inside of a computer by sampling or measuring the amplitude of an analog waveform and storing these measurements away as binary data. It does not depend on the pitch, the tone, the frequency of the signal. We are simply measuring the amplitude of that. Like images, If we sample more often, or the range of the numbers that we represent, they get larger, the quality can be improved, but so will the size. So if we end up with really large files, what can we do? We can compress them. Two types of compression, lossy and lossless. Lossy is used when we are able to lose some of the content of the data and still be able to use it. So images and sound, perhaps, they might not quite look as good as they did, but with a much smaller. Lossless is a type of compression where we make the files smaller, but we're always able to get back to the original value. For something like a text document, emails, spreadsheets, etc., we would need to use lossless compression. Next topic is computer networks. We need to know about LANs and WANs. So a LAN is a local area, where it covers a small geographical area network. A wide area network is a larger one, covering a larger geographical area. More often than not, WAN is used to connect local area networks together. You need to be aware of factors that affect the performance of networks, such as bandwidth, which is a measure of how much data can be sent down a network at a given time, and other factors such as latency or the number of users that are using a network. There are two ways computer networks kind of fundamentally work. One of them is client-server, where the programs such as, say, a web browser requests a service from something like a web server to ask for some web pages. We have another type where we have peer-to-peer networks, where all of the devices in that network share their services between them and advertise what they can do. So, for example, you might have a printer in there in a network that other devices can use, or storage devices that other devices can use without using a server. Need to be aware of all of the different pieces of networking equipment in a local area network. Wireless access point obviously gives us Wi-Fi access, so we can connect things like laptops and phones into a local area network. Note that a wireless access point is not really connecting us to the internet. It is simply replacing wired connections such as Ethernet. It is routers that will give local area networks access to the wide area network. Inside of a local area network, the device that normally connects all of the devices together when we're using Ethernet is something called a switch, and all of the devices would need to have a network interface card of some type inside of them to allow them to connect to the switch. Have different types of transmission media for local area networks. Ethernet is the most popular. When we move to wide area networks, then sort of such as the internet, we need to understand a little bit about how web servers work using domain name servers. So in order to address computers on the internet, we have IP addresses, and these are addresses that will uniquely identify computers on the wide area network, but they're not very user-friendly for humans. So when we type in something like www.bbc.co.uk, that is a domain name. So when we're doing networking for web pages, we need to be able to convert those domain names into IP addresses, and that is called DNS. When we store files such as web pages on a computer that other devices can connect to, we call that hosting. Also, we call the cloud, where we're sort of moving lots of services and things away from local area networks such as storage and email and things into the cloud. Need to understand a bit about physically how the networks are connected together. The two most popular topologies are the star and mesh network. Star is probably the one that's more popular. It has a switch in the middle. So if you're asked to draw a picture of a star network, please make sure you don't draw a client-server networks architecture. It is a switch in the middle for the star, a server in the middle if you're talking about client-server systems. Modes of communication, main two are wired and wireless. We need to know about those. Encryption, well, we want things to be secure. Need to know the difference between IP addresses and MAC addresses. Need to know all of these common sort of protocols and what they're used for. And the idea that we split networking up into layers. It's a big, complicated system, networking, and we have layers that are responsible for different parts, maybe the physical bits of connecting things together, addressing of things with the network layer, the way of packetizing data to split it up in the TCP layer, the transport layer, and then our applications such as email, file transfer, HTTP, etc. for web pages. Having computer networks enables us to do lots of different things, such as communicating and sharing information and data, etc. Downsides, though, of networking is it is easier for people to attack computer systems because the networks are all connected together. You need to know about the different types of malware. So we've got viruses, we've got Trojans, we've got worms, we've got adware, we've got ransomware, and you need to know about social engineering, how this is where perhaps people get sent an email asking to change their passwords, when in reality the site they go to change the passwords is actually a fake site. Brute force is where a system will repeatedly try and use passwords and sort of generate different passwords quickly. That's why we need to have long and secure passwords. Denial of service attacks, where computers will repeatedly send requests to servers and eventually stop them from working. If we don't encrypt our data, then it can be intercepted. And we have this idea of SQL injection, where we can send data to a server that's communicating with a database, and the users can sort of send it in such a way that if it's not tested for, it can cause the instructions on the database to be executed that we wouldn't want. As well as knowing the forms of attack, you need to be able to understand about the ways we can stop these. Penetration testing, where people deliberately try and test networks for security to see if they work. Installing anti-malware. Firewalls, which is a software or hardware device that tries to stop any unwanted traffic accessing a network. User access levels, where different users in a system may have different levels. So, for example, some users may have read and write access to certain folders, where other users might have only read access. We need to use passwords. They need to be good and strong, so they can't be broken with brute force. We need to use encryption so that data can't be intercepted. And finally, businesses should, where possible, include physical security, locks on doors, etc., to stop people from accessing their systems. So far I've talked a lot about hardware, and I've talked about the idea of having application programs which we fetch and decode and execute, but there's another layer of software that is used inside a computer called the system software. And these compose of either the operating system or utility software. The operating system, such as Windows or Linux or macOS, it has some functionality. It provides a user interface, it manages the memory of the computer and allows multitasking, so we can have what appears to be multiple programs running at the same time, allows us access to devices such as printers and things, allows computers to have different users and sets up and stores usernames and passwords, and provides us a common way of interfacing to storage devices, so that to the user, they have no idea if it is a hard drive or a solid state drive that files are being sent to. They see a common interface through something like a file manager. Normally an operating system will be shipped on a computer, but we can also have additional pieces of software which come either along with the operating system or can be added. It's not the core of the system, so they're called utility programs. They're applications that you would run that aren't really the same as running things like word processing applications. They're ones that are used to help maintain the computer, such as encryption, so that data, if a hard drive, for example, was stolen, the data on it could be encrypted so people couldn't access it. If you're using magnetic hard drives, the way they operate means that sometimes files got split all across the surface of the disk, which can slow the hard disk down. So we can defragment the hard drive and move the data so it's in a contiguous areas on the surface of the disk, making it faster to be accessed. We talked a little bit about compression earlier and how this might be needed for things when we've got lots of data being stored, particularly images and sort of text files and things that are large. Therefore, we can have utility programs to do the compression for us. And finally, the last topic we need to know about is ethical, legal, cultural, environmental impacts of technology. Obviously, all of the things that we're doing here with computers, we would like to try and do things ethically. So that means that if what we are doing is going to harm other people in a way, it doesn't necessarily need to be illegal, but we need to think about what is right and wrong when we're using computer systems. Obviously, computer systems have allowed people to do things which would be illegal, such as stealing data, etc. We need to be aware of these. Cultural, different parts of the world, different cultures and different religions, countries, etc. They have different views to other people around the world, and something we need to be aware of when we're developing systems. Finally, all of the hardware and all of the energy that's used to build computers and to run computers, where possible, we need to sort of minimize the waste of computers and how much energy they use. We're storing lots of data about people and users and systems and things. We need to try and make sure this is secure, and we need to make sure we're not sort of invading people's privacy by allowing people to access this data. So because of all of these different issues, some laws have been enacted over the last few years. You don't need to probably remember the dates, but you need to remember the ideas of them. Data Protection Act, this is to do with privacy issues. Computer Misuse Act, this is to do with using computers in a way that is unacceptable. Copyright, design and patents, this is about not using other people's images, films, ideas, etc. And finally, that there are different ways that software can be licensed, such as open source and proprietary, and understand, be able to weigh up the benefits, advantages and disadvantages of each of these two ways of software licensing. So I hope you've got all the way to the end here to hear this. Unfortunately, it's been longer than I thought. If you've got as far as this, I just want to say good luck with your exam.